At the very front of logical progression is the European Gathering for Atomic Exploration, CERN, eminent for its notable commitments to molecule physical science. As of late, the widely popular Molecule Physical Science Research Center has uncovered a very intriguing finding from its Large Hadron Collider that could totally change how we might interpret the universe. Researchers accept these odd discoveries could reveal the presence of outsider life in an equal reality. This historic thought has ignited fervor and extensive conversation among specialists. Could this astounding disclosure reshape how we might interpret the universe? Furthermore, whenever affirmed, what significant bits of knowledge will this revelation offer into the nature of reality itself? Join us as we dive into the recently distributed findings, exploring how CERN researchers are ending their silence on this chilling new revelation that has the potential to change all that we know. The European Council for Nuclear Research, otherwise called CERN, has been renowned for its thrilling tests since its commencement during the 1950s. It has been in the spotlight several times for good, yet its investigations have stimulated concern about the potential development of black holes, fractures in our reality, and numerous other threats. One of CERN's most famous and disputable accomplishments was the development of the Large Hadron Collider (LHC). The LHC is the world's largest atom smasher, beginning operation on September 10, 2008, and remains the latest addition to CERN's accelerator complex, spanning more than 27 kilometers of superconducting magnets and a progression of accelerating devices. The CERN super development cost more than $4.5 billion. Many would argue that this money was wisely spent, as the LHC has brought about some of the most significant disclosures of the last few decades, such as the discovery of the Higgs boson and numerous other previously unknown particles. This enormous machine is capable of speeding various particles around the circle until they reach close to light speed and complete more than 11,000 laps per second. The LHC does this with an arrangement of exceptionally powerful electromagnets that produce a magnetic field inside the accelerator that is nearly 100,000 times greater than the field that encompasses the Earth. Some have expressed concern about the impact of creating such a strong magnetic field on nearby devices, as well as its effect on the Earth's own field. Once these particles reach their maximum speed, nearly the speed of light, particles heading in opposite directions are compelled to meet in a brutal crash, releasing enormous energy and a variety of particles. When particles collide, a surge of particles escapes in every direction, with most of them enduring only fractions of a second before fading. Changing the source of particles allows researchers to uncover new particles. In this whirlwind, uniquely created ultra-sensitive detectors are installed around the collision sites to record all the information from each impact. This amount of data mounts up quickly and requires a significant amount of time and work to process consistently. The LHC's experiments generate more than 15 petabytes of raw data from these impacts, which must be purposefully analyzed to extract the information the researchers need. In 2017, the LHC achieved a significant milestone by permanently storing more than 200 petabytes of data in its tape libraries. To put this amount of data in perspective, 1 petabyte is practically equivalent to around 250,000 movies. But what exactly are they searching for in all of this data? They identified something significant with a particular kind of quark. Quarks are the fundamental building blocks of matter and exist in various flavors, as defined by physicists. Some of these quark flavors are very unstable, decaying into other particles in the blink of an eye. The beauty quark, with an average lifespan of 1.2 trillionths of a second, became the focal point of attention due to a specific variation. Its decay pattern differed from what researchers anticipated based on the standard model. According to their predictions, when a beauty quark decays, it will be affected by the weak force and transform into a set of lighter particles known as leptons, either an electron or a muon, with the standard model predicting a 50-50 probability for the two particles. However, the LHC data revealed that these quarks decayed into muons 70% of the time, as opposed to electrons. This discrepancy could exist if a previously unknown kind of particle is involved in the process. This has led some academics to think that some new type of physics may be at work. A new force-carrying particle would imply brand new material science that could expand the standard model and answer many confounding questions. The possibility of new physics challenges the standard model theory, which provides our best understanding of how the strange world of particles behaves. The Standard Model is a scientific framework that precisely explains every aspect of our knowledge of the physical world's building blocks. The amazing thing is that, despite this high level of accuracy, physicists are well aware that this model is still incomplete. The Standard Model only describes three fundamental forces: electromagnetic force, strong force, and weak force. There is currently no representation of gravity force or an explanation for dark matter, the universe's pervasive type of matter. During recent trials, scientists found a discrepancy in the data they were evaluating that differed from what is standard. Although it is not uncommon to find results outside this framework, given the volume of data produced by the LHC, this time something piqued researchers' interest, and they saw the need to investigate further to determine this new occurrence. What might this pristine force be? To explain this unexpected revelation, the researchers proposed the presence of another fundamental particle, which they refer to as Z', a force-carrying particle. Despite the fact that this force is believed to be very weak because there have been no indications of it until now, the researchers believe it would interact differently with electrons and muons. Yet, the extent of its interactions with Standard Model particles remains unknown for the time being. Assuming researchers found new force-carrying particles, it would be a long-awaited breakthrough in material science. Physicists hope that if this discovery is confirmed, it will help unravel long-standing mysteries of the universe and provide insights into age-old problems, such as what dark matter is and the Higgs boson's role. In the present day, some researchers believe that this unseen force could help fulfill one of physics' most significant goals over the last century: unifying the fundamental forces of existence. According to Elon Musk, CERN built the largest and highest energy particle collider in human history, the Large Hadron Collider, between 1998 and 2008. More than 10,000 researchers, many institutions, and labs from over 100 countries assisted with this process. It sits inside a 27 kilometers long tunnel on the border between France and Switzerland, near Geneva, around 175 meters underground. The very first collision recorded at the Large Hadron Collider had an energy of 3.5 tera-electron volts per beam, approximately 3 times that of the previous world record. The energy reached 6.5 tera-electron volts per beam once the LHC was further upgraded. Musk noted that the Large Hadron Collider excels at proton beam collisions. Besides, it can accelerate lead-ion beams as well. Specifically, every year, proton and lead collisions are conducted for 1 month for researchers testing the predictions of several particle physics theories. The main goal of the Large Hadron Collider is to test the properties of the Higgs boson and look for the large group of new particles predicted by subatomic particle theories. Hadrons are composite subatomic particles made up of quarks that are held together by a strong force, much like how atoms and molecules are held together by the electromagnetic force. Protons and neutrons are two examples of hadrons that are widely recognized, including the pions and chons, which were first discovered in cosmic ray experiments in the late 1940s and early 1950s. The LHC brings two creating particle beams together so they can collide. The Higgs boson is thought to be an elementary particle associated with the Higgs field. It is the quantum excitation of this field, like how you notice ripples in the ocean. The boson resembles a brand new species in the particle zoo. It lacks the quantum characteristics of fundamental matter and the carriers of quantum interactions, like electromagnetic force, weak force, and nuclear interactions. The Higgs boson was found at the Large Hadron Collider, a pivotal finding achieved simultaneously by the two major multifunctional experiments, ATLAS and CMS. It was announced on July 4, 2012, at CERN. At the time, the new scalar boson was found primarily in two rare decay channels that provided the purest signal: decay into a pair of photons, which required an absolutely quantum virtual process, and direct decay into a pair of Z bosons, the carrier of the neutral weak interaction. Although the finding of the Higgs boson at the time established the Standard Model, examination into this elusive particle didn't end there. One of the main discoveries since 2012 was the confirmation of Higgs decay. According to CERN, at the time, the examination into this elusive particle would expand during the LHC's third cycle, especially once the particle accelerator's high luminosity upgrade is completed in 2029. This will allow the LHC to attempt more collisions, giving researchers greater opportunity to detect rare physics, such as events that don't fit into the Standard Model. CERN estimates that when the accelerator is updated each year, it will produce 15 million of these particles. This compares to the LHC creation of 3 million Higgs bosons in 2017. This may be helpful for identifying different types of the Higgs boson, including speculations that go beyond the standard model of particle physics. Expect up to 5 distinct forms of Higgs bosons, some of which may be created less frequently than the fundamental Higgs. Even before the enhancements, researchers have produced convincing evidence of a magnetic Higgs boson. But why should this matter about the Higgs boson? The Higgs field was incredibly significant and fundamental in the universe's very existence, particularly in the aftermath of the Big Bang. The field provided mass to elementary particles, which allowed more complex particles and eventually atoms to form, leading to the stars, planets, and the emergence of life itself. The Higgs boson is also expected to decay in other forms, such as dark matter particles. This goes beyond what CERN already found, but this hasn't happened yet. Scientists believe that dark matter exists in equal parts with normal matter, but it hasn't been found yet. Observing Higgs bosons directly decay into dark matter would be a major advancement in this direction. Given the increased data production capacity of the upgraded LHC, researchers are optimistic about finding additional Higgs bosons and resolving some of the universe's biggest riddles. Many mysteries remain to be solved, and there is much work ahead for physicists working at CERN. Researchers at CERN, with their cutting-edge technology and collaborative efforts from around the globe, are poised to unlock even more secrets of the universe. The upgraded LHC, with its increased energy capabilities and enhanced detectors, is expected to delve deeper into particle interactions and potentially discover new particles beyond the standard model. One of the ongoing pursuits is the search for dark matter. Despite its prevalence in the universe, dark matter remains elusive and mysterious. Scientists hope that the LHC's experiments, particularly those involving the Higgs boson, may provide clues or direct evidence related to dark matter particles. Moreover, the exploration at CERN extends beyond fundamental physics. The technological advancements developed for particle accelerators often find applications in various fields, from medicine to material science. Techniques pioneered at CERN have led to advancements in medical imaging and cancer treatment, demonstrating the broader impact of fundamental research. As CERN continues to push the boundaries of our understanding of the universe, the international scientific community eagerly awaits the next breakthroughs and discoveries that could reshape our understanding of physics and the cosmos itself.